Hey guys, let's talk about the settings in the VESC tool. This is not a tutorial for new users. There are plenty that show you how to set up a board. Instead, I want to go over each of the settings that are available in the VESC tool. So let's start with motor settings. And this is targeting Onewheels mainly. So for eSkate and so on, some of this will not apply. So motor settings general. Let's start here in the main tab. Motor type should always be FOC. You shouldn't mess with that. Invert motor direction. That is something that you would touch if your speeds are negative. Let's say you're riding forward, speeds are negative. Then you would have to flip your IMU orientation and also change the motor direction. Otherwise, don't mess with it. Sensors. This tab does not apply to us. Current. This is an important one. So here I will start with the battery currents. The battery currents are what you set according to the battery that you have. If you have a battery that's capable of outputting, let's say 90 amps, like the 18S2P packs with the big 21700 cells, they are rated for 45 amps each, so technically 90 amps. However, typically for a pack like that, I personally prefer to set it to something reasonable like 60 amps or so. More than that just doesn't make any sense. And for regen, I would set a little bit less typically just because you never get that much regen current out of a battery anyway. So 60 minus 50 would be the most that I would set for those beefy packs. But because I am connected to a board with a stock XR pack, I am using these settings right here. Current scale, this is for eSkate only. Make sure it stays at 100%. Slow apps, current limit, we keep that at false typically. There are situations where some people are setting it to true, but I would not recommend doing it. If you have a good controller, you shouldn't need to set that to true. Now the motor currents. Keep in mind that motor currents tend to be much higher than battery currents. So even if you have a battery capable of 30 amps, your motor currents can be easily 120, 140 amps, because at low speed, motor currents tend to be much, much higher than battery currents. So 120 is a value I like with a little Fokker. Some people go up to 140, 150, and the only way you would notice the difference is if you're doing tricks. You tend to get a slightly more responsive board, but on the other hand, people that do tricks also tend to like lower motor current so that they can nose drag and so on. But it all depends on your controller as well. So if you have, for example, a U-Box, then 100 is the safe maximum for the U-Box 100. If you got the 80 that's rated for higher amps, then you can go higher as well. But this comes down to personal preference. Less than 100 is rarely useful, and more than 150, even with a Tronic X12, doesn't really give you much of an advantage. I think I've set 160 for my X12 now, but I barely ever hit that kind of limit. Now, for braking currents more than 100, I don't think that you'll be able to notice a difference if you go higher, so I just keep it limited to that. Absolute maximum has to be 50% higher than what you set the motor current max to. So for 160, you would want 240 and so on. But I had 120, and then I was just lazy and put 200 in there, but 180 would be sufficient. Next one is voltage. These are your voltage cutoffs. Your tutorials tell you how to set that, but it's basically 2.7 times the number of cells for cutoff start and 2.5 times the number of cells for cutoff end. That's it. And the battery filter constant is used for computing the battery percentage in the VESC tool. So I like to have my value a little bit higher so that voltage spikes and voltage sag doesn't affect it so much. So I like 60, for example. Then RPM limits. Typically, you don't want to mess with it. You definitely don't want to use that to limit the maximum speed you can reach, because if you were to set this to, let's say, 10,000, then that would translate to about 20 miles an hour, and bind it with the default 80% ERPM limit start, so you really get that at 80% of 20 miles an hour, which is about 16, it would start throttling the maximum currents it allows, meaning it limits your ability to balance, and at 20 miles an hour, your nose would just simply go down as you push forward. So you want to use tilt backs in the float config for this, and the only legitimate reason to use this feature here is when you're doing tricks and you want to limit free spin. But then you got to be careful to remember to crank it back up to something above the speeds you would ever reach, like this would be 40 miles an hour, when you're done doing tricks. So use that with extreme caution if you do. Wattage, we do not limit wattage. Temperature, this is another important one. Here, you want to make sure you don't use the default. The default is 15%, and you want to set that to 0, because, again, we're not using the normal mechanism by throttling currents when you reach these temperatures. Instead, we are relying on tiltbacks when those temperatures start. So here are the values that I'm using, and the rest you don't want to touch. For the superflux, you want to double check what the thermistor value is for hypercore. I think this is correct. The next tab is BMS. I set that to none because I don't have a VESC compatible BMS connected via CAN bus like the X-Lite from Enoid. But if you do have one connected, you need to set it to VESC BMS, and in that case, you want to turn off overtemp and SOC protection, because again, this is something that is not meant for Onewheels. You don't want to get shut down when the VESC reports an error. When the BMS reports an error. Then there's the Advanced tab. Here, minimum and maximum voltage. Do not mess with it. Leave the defaults, because this is not related to your battery. This is more related to the capabilities of your controller, so don't touch it. Also, minimum maximum duty cycle, I wouldn't mess with it. I did in the past, sometimes when I wanted to sort of get the maximum possible out of my controller, I increased this to 96 or 97%. Probably doesn't make a lot of difference, but keep in mind you need to keep a reserve of at least 3 to 4% depending on the controller for your motor calculations. So you can't use 100% of the duty cycle. If you do, the tool lets you set it. I think you can do 100% here. If you do that, then dangerous things can happen, and they will happen at full speed, so you don't really want to find out what happens. I would say 96, 97, let's say you're racing and you want to get the maximum possible speed. You can try 97, but anything higher than that, I would definitely not do. The other settings I never mess with. There are some people that are reducing the fault stop time. Again, this is something that if you have a good controller that doesn't have any issues, you shouldn't have to mess with it. So this was the easy part. Now comes FOC. FOC is where it gets more complicated. Here in the General tab is where we have our key values. These get determined by the motor wizard when you run that, and the only thing that you typically change would be the observer gain. And if you have issues with crunch noise at low speeds, then this is typically something you can tune with some of these values. I will not go into detail. There is a crunch guide on pev.dev. You may want to follow that, but here are the different values that you want to change. This has to say Hall sensors, then resistance and inductance. Make sure that your values are within 10% of what other people have for your motor. Inductance difference, there we get a lot more variation. People get from 15 to 50 or 60 microhenry here. If you're outside that range, then you probably have some other issues as well. Then the motor flux linkage, this is something that tends to be within 5% or less of everybody else's values. So flux linkage is something that you want to find out what other people have with the motor that you have. This is a MK1 superflux, so this is the typical value that you would see, something close to 24. And then KP and KI tend to be a reflection of the inductance and resistance. Motor resistance, you can see here, is 30.6. Current Ki is also 30.6. That is not a coincidence. That is what the wizard determines. And for inductance, it is similar. So this value, 107.84, you can recognize here as well. Now these values can be manually played with as well, but I refer to the crunch guide on pev.dev for details. Also, since I have this tab open, you do have the option here to rerun motor detection without using the wizard. And that's personally my preferred way of redetecting the motor. I run the wizard once in the beginning with a new setup, but once I have my setup done, then I prefer to do it through here. It doesn't change any values outside of this tab. And in fact, it doesn't change any values at all until I hit apply. Whereas the wizard, it just makes a whole bunch of changes and you always have to go in and correct some of the values that it sets. So this is pretty convenient, and I have a video that explains how to do this. You basically press this button, then you press this button. Obviously the motor will rotate, so make sure you have nothing in the way. Also make sure that the float package is disabled so you don't have brake current getting in the way of this. And this allows you to redetect motor values. Then the next tab is Sensorless. It doesn't apply to us. Don't change anything in here. Now there is one more setting that I forgot, and that is in Sensorless. So I was lying when I said that this doesn't affect us, because recently somebody discovered that if you have crunch issues, so transition behavior issues from censored to sensorless, then adding the saturation compensation mode, you want to use factor, and adding 10 to 20% in here, that will help with the transition behavior, specifically for hypercore motors, because they do saturate easier than, for example, a superflux or a cannon core. So play with this if you have transition issues. Hall sensors, this is where you would make sure that you have 2000, or some people use less here. I've had good results with anything from 1000 to 2000 with hypercores and superflux motors. Then Hall interpolation ERPM, that needs to be about half of the default value. Default is 500. I like to have 200 to 250. And then the rest are your Hall sensor values. Also, here you can rerun the Hall sensor detection if you want to. Make sure the motor can spin, and then you get new values, and then you can apply them. But you got to remember, if you run this here and you hit apply, then it only copies the values up here. Then you still have to press this button to actually write the motor configuration. So don't forget that. It's a two-step apply process, basically. All right, encoder doesn't apply to us, HFI doesn't apply to us, VSS doesn't apply to us. Filters, that should be set correctly for whatever your controller is, so the default firmware settings should be good. Offsets, by default, this is set to true, which means that on boot, it spends about 2 to 3 seconds recalibrating, redetecting those offsets. And once these have been detected, you can just save the settings, set this to false, and accelerate or reduce your boot time a little bit. So I always have that at false after the initial couple boots. All right, the next one is field weakening. This is a very important feature, and the tutorials will tell you to set this from the default 0 to something like 30 to 50 amps. I have it set to a fairly aggressive 40 amps here for a stock XR battery pack, and I haven't had any issues, but I also don't tend to push maximum speed. I just have that sort of as a safety margin for being able to go 20, 22 miles an hour with this setup. This is a Superflux-based board with a stock XR pack. The next one is duty start. You want this somewhere between 50 and 70. I tend to do 60 to 65. And then the next one is the ramp time. One thing I noticed is that when I used some of the recommended values, like some people said, oh, you got to set this to 1,000 so that you don't feel some nose dip when you're transitioning into the field weakening territory. I never felt these nose dips, but I also don't accelerate super hard into high speeds. But what I did notice when looking at detailed logs is that this long ramp time, when you're actually needing it, causes the field weakening to come in with a delay, with namely 1 second. So if your duty cycle jumps from 80% to 95% because you hit a rut or something, then while you're going fast, then the ramp time here would prevent the algorithm from giving you all the field weakening that you configured. So you might be stuck with just 20, 25 amps of field weakening, so your duty cycle will increase even more, and you will not get the full effect of the field weakening. So it is not necessarily a good idea to just go higher here. I have been riding mostly with 300 or so on my other boards. This one I haven't touched in a while, so it was still at 500, but I prefer something like 300 milliseconds for ramp time. Now the advanced tab. So here are a few important ones. One is the zero vector frequency. What our boards experience very often is interference or resonance effects between the motor control algorithm and the IMU update frequency, which cause potential nose hunting, nose dips. And so you want to find the right zero vector frequency for your setup. And very often just making changes by 1 kilohertz or even a half a kilohertz can eliminate these nose dips. So this is something you want to play with. Also, what we did notice is that much higher values, you can go up to like 40 kilohertz fairly safely, but on some controllers, this will cause noticeable increase in heat up of the controller. On the Thor and the X12, this has not been the case. I've been riding my Thor with 39.5 kilohertz. I did get nose dips at 40 kilohertz, so I went back by 1 kilohertz, and I actually settled on 39.5. But for little Fockers and Tronic 250Rs, I find going higher than 30 kilohertz does have a noticeable impact on the controller temperatures, so I prefer to find something that is more around 25 kilohertz. But again, this is something you've got to experiment with. The other values here you don't want to mess with. And then you have the observer type. So this is something that nowadays defaults to MX Lemming lambda comp. If you're experiencing motor crunch in the transition, then you would go and set that to either Ortega or Ortega lambda and try it with that. Some people have reported the best results with Ortega lambda. The main reason why this board was still on Ortega Original and not on MX Lemming is because this is a board I've had for a while now, and I set it up on 5.3 and 6.0 where the default was still Ortega Original, and I didn't rerun motor detection. I just kept it as it is because it was working perfectly. I had no reason to rerun the detection. So I'm still on this. That doesn't mean that MX Lemming Lambda wouldn't have worked. Then there is MTPA algorithm mode. This is a new feature that we used to consider unsafe for Onewheels, and it did have some nasty bugs in it that made it pretty dangerous. However, I'm hearing from some users, namely Hannes, aka VESC Man. He says that he turned this on to IQ Target and reports some improvements that he noticed. I don't remember exactly what, but he still keeps field weakening on as well. So I'm not quite sure. This is something that if you're unsure, I would just keep it on disabled. If you're adventurous, you may want to try turning it on and report back how it goes. And that is it for advanced. The other settings we don't mess with, except that additional info, which is purely informational and used for battery capacity calculations. It doesn't affect your ride at all. It's also used for speed calculations. So here you want to make sure you got 30 for motor poles, 1.0 for gear ratio, and then a correct wheel diameter, which I wouldn't bother measuring your wheel. I would just look at the GPS numbers and then adjust this number until the GPS speeds match your VESC speeds. And then here the battery cells in series and capacity and so on. All right, moving on to app settings. We're almost done. Here in general, most people won't need to touch it, but if you do, you want to make sure app to use is UART. The VESC ID is the ID of your controller, also called the CAN ID if you're working with devices connected on the CAN bus. Then you have pairing done. This is a treacherous feature. Be careful with it. If you're pairing your phone to your controller, then this would be true, and that means you can no longer connect via Bluetooth from any other device. And you can get yourself in trouble with that. I'm not going to go into details, but I would highly recommend making sure that this stays false. Shutdown mode. This is interesting only for devices that support momentary switches like the new Thor 300 and maybe some other controllers in the future as well. But here you can change how quickly it powers off on its own. Then this is it on this tab. Then we have the IMU, and here you also typically don't need to go in to make any changes because the IMU wizard sets it up for you. But in here, IMU type should be internal unless you have something externally connected on a FlipSky module, on a FlipSky controller. Then the sample rate, that needs to be 800 for any device with a BMI 160, like the Little Fokker V3.0 or a U-Box, and it needs to be 832 for the LSM6 devices, like the Little Fokker V3.1, the Tronic 250R, and a few others. This gyro accelerometer filter essentially lets you choose between 3 different settings of the hardware of the IMU itself. So this is basically letting the IMU chip do some filtering itself. Medium works best for most people. Then there is the low pass filters. Here we typically only use the Z filter, and you want to set that to 1.0 for avoiding the nose dips. So before we had that, this is when we had the nose dip issues, and Mitch introduced this feature and that fixed it. Then here, the AHRS mode, that should always be Mahoney, and then Mahoney KP will be whatever. 2.0 is the default for us, but if you want a stiffer board, this will be lower. If you want a softer board, this will be higher. But I recommend changing this from the float package, not from this page. This accelerometer confidence decay that I skipped over, that is a feature that doesn't need to be touched, but it needs to be set to 0.01, and that will be done if you run the wizard correctly. So the default is 1.0. That we do not want. 0.01 is the best value for us to use. And then the only other thing that you may want to play with, if you switch from straight rails to angled rails like W rails, then you can make changes in here without rerunning the IMU configuration wizard. So for example, if I add angled rails 3 degrees, then I could change this to 5 degrees, and that should take care of it. However, because of the orientation of the IMU, so if you have a 90-degree offset, then it's not the pitch that you would change, but it would be the roll that you change. So best is to make changes in 1-degree increments, ride the board, see how it feels, and this way you can adjust your the way your nose feels. And I would recommend just making sure that your board rides the same in both directions, then you know that you have leveled it properly. This is it. Those are all the settings that are relevant to us, and I hope this is helpful.